So,
Hi.
thank you everybody very much for coming. This is the first CAMS colloquia of our new academic year. And in fact, it's the first in-person CAMS colloquia for now 3 years. So it's a new experience. And as you see, we needed a little technological help, which now I believe we have got. And we are delighted that Nathan Glatt-Holtz will be here in person to give our first in-person CAMS colloquia. So Nathan, as a number of you, I believe, know, Nathan is one of our very distinguished former graduate students, and very pleased to have him here again. And he is now professor at Tulane University, and he will be talking on a unified framework for Metropolis-Hastings Type Monte Carlo methods. Thank you, Nathan.
Okay, thank you to everyone, to Susan, the CAMS colloquium, and just so many old friends, like my thesis advisor in the audience. Anyway, it's lovely to be back. We had a few technical hiccups, but I think hopefully this will go through. Can everybody hear me? Because I'm not wearing the microphone. I mean, out in TV land or whatever. Okay.
Yes.
So good. So is this, okay, it's not in the way over there. Good. I'm sorry, I'm still figuring out. I just want to get this out of the way. Okay, so I want to talk to you about a sort of grand unified theory, as it were, that we've developed for a class of statistical sampling algorithms. This sort of came out of a wider program that we've been working on for a few years now on PDE, on sort of statistical methods for parameter estimation in PDE models. So I want to sort of start by stepping back and tell you what the statistical sampling problem is and a little bit about our motivations. I spoke here over Zoom about a year ago, so I just sort of spend a minute or two kind of reminding you of this wider program, and then we'll talk about this theory and how it plays out over sort of some quite classical algorithms and then some newer methods, including, and the thing that's exciting about this theory, other than sort of illuminating a lot of really pleasing and beautiful underlying structure to this class of algorithms, it's sort of provides a methodology for deriving new methods, which we're quite hopeful will be like efficacious. And so we'll show how this theory derives some interesting new methods, and then maybe end with some numerical case studies. And the main references are these two papers in reference. Let me just quickly acknowledge if it'll let me change screens. What is going on? Let's see if I can. I just want to see if okay. I just want to acknowledge some collaborators. I'm actually here this week visiting Andrew. We've never met in person, so that will be a nice opportunity this week. And Justin's my former PhD student, who's a professor at Virginia Tech. Cecilia Mondaini, who some of you may know, was a postdoc with me and is now at Drexel. So they've been my partners in crime in this whole business. Okay, so what is this problem? It's very simple to state. You have a probability measure. You can have it on sort of an arbitrary measurable space. And really, we want to compute various moments, various observables of this measure. So if you were sort of halfway paying attention in Peter's probability class in graduate school, this is really an integration problem. But there's a number of reasons why this is a very challenging problem computationally. The parameter spaces we're interested in are often high or infinite dimensional, and some model problems we're talking about, you want a probability measure on, say, classes of functions, so infinite dimensional spaces, and your measure mu is very often not a standard distribution, so there aren't really analytical solutions to these things, and think that mu is multi-weld and it's numerically expensive to evaluate these integrals. So this is sort of at the core of what makes modern Bayesian statistics go along, but this is sort of a ubiquitous problem that comes up throughout chemistry, statistical physics, etc. And just sort of leave aside the idea that you'd be using sort of quadrature deterministic techniques to evaluate this integral. So the core idea for these type of problems is to use Monte Carlo methods. So you probably saw something, I remember seeing this as a starting graduate student, this basic idea that say I want to evaluate the integral, say 0,1 of f of x dx. And so one way to do this is to just draw a sequence of IID uniform random variables. And what I would do then is just take an average, and by the law of large numbers, let's say, this will converge as n goes to infinity to the integral you want to compute. So more generally, if I have a Markov kernel, which is just a gadget, which for every point in my state space gives me a probability distribution in a sort of measurable way, I'd like to find a Markov kernel so that if I draw from it repeatedly by some ergodic average, I'm going to converge to the integral I want to compute. Okay, so I'm approaching sort of early middle age. I feel like I'm becoming a walking dad joke, but I love this little line from South Park. Well, okay, so use Markov kernels, great. And if you find the right one, it'll do this, but how do we find the Markov kernels that are going to actually evaluate this integral, that are going to be sort of ergodic with respect to, we always refer to these sort of in the business as the target measure. And just feel free to interrupt me with questions, comments, concerns. Okay, so this is a beautiful idea going back to, I guess, the late 1940s, early 1950s with Metropolis and his group. And then, so how do you go about this? So you sort of carry out finding a good Markov kernel in a sort of two-step process. So you have what you call a proposal kernel, which is some distribution you can draw from conveniently. And wherever your current state is, you draw from that. And then, of course, your proposal kernel is not going to be unbiased with respect to your target measure in general. So you can correct for that by very carefully selecting a probability that you're going to accept or reject the proposed state. And you flip a coin with that probability. And if it's, say, heads, you go to the new state. And if it's tails, you stay where you are, and then you try again. You just do this over and over. Okay, so I'll show you a nice little video. Maybe it'll work. Okay, so we're drawing little Gaussian draws around the current state, and you can see it being averaged out, right? And you can see that if your proposal kernel is symmetric, these two terms cancel off. So basically, if I go to a higher probability region, well, I just go there. And if I end up in a lower probability region, I go there with a probability proportional to how much less likely it is, and it works. Okay, and so this is kind of the starting point. So everything I'll be talking about today has this kind of structure that you have a proposal kernel, and then you have an acceptance probability, and you have to figure out what the acceptance probability is. Right. Is it going to let me move on? Right. So then, okay, so I've written it in this potential form. Here's my target measure. So there's all these different approaches to having sort of good proposals. The one that I just showed you, going back to Metropolis, let's say we draw, Gaussians around the current state. All right, so that's a sort of random walk approach. But then later in the sort of 80s and 90s, you start to have a dynamical systems sort of point of view, which is, okay, so you have this target measure and you identify different types of dynamical systems that are going to hold the target measure as an invariant, right? So we'll sort of go into some details in this, but both in terms of sort of stochastic differential equations and Hamiltonian dynamics, you have certain types of dynamical systems that are going to hold this target measure as invariant. And then, of course, you can't just simulate these directly. You have to do various sorts of numerical discretizations, and then you use the metropolization to correct for the bias that comes in the errors that are made. And then an idea that we'll come to at the end of the lecture, sort of, actually strongly motivated by the type of architectures in modern computers, GPUs and so on. You want to, from the current state, generate a cloud of proposals and accept from that cloud of proposals with different probabilities. Okay, so this is nice for all sorts of things with parallelization. Okay, so these are sort of like, in a thumbnail, some different ways in which you can carry out this strategy in various guises. All right, so I spoke at some greater length. There's a problem speaking somewhere in short succession on this motivating problem, or motivating sort of research program for this work, which is a sort of Bayesian approach to estimating parameters, in particular infinite dimensional parameters in partial differential equations, often motivated by fluid measurement problems. So you think you have a parameter function that's defining a PDE. I'll give some concrete examples in a second. And so the parameter defines the PDE, which gives you a solution, which then you observe, let's say at some points, let's say in space and time, for example, just for example. And then you want to, and that gives you data in essence, and you'd like to, in effect, invert this G to figure out what your parameter is. And for all kinds of reasons, you wouldn't expect that you could invert this G. And moreover, your observations are often polluted by a degree of observational noise. So the sort of Bayesian approach to inverse problems is to treat this as indeed as a Bayesian problem. So I put a prior on my parameter, and I treat sort of y given u as a likelihood, and putting this prior, I get this posterior distribution. I think an easy way to think about this is I have some kind of objective function that is happy when g of u is near the data, and it has a sort of soft constraint put on it by the prior. Let's say, in our case, like degree of regularity or other things that we might know beforehand, and then we're really just trying to draw a heat map, which tells us sort of something about high and low probability regions according to this objective function, or high and the high probability regions are making the objective functional happy, let's say. Okay, so this is a very nice way to deal with all sorts of interesting PDE inverse problems, ill-posed PDE inverse problems. And I may have spoken about some different model problems we've been thinking about intensely, which will sort of serve as a backdrop for the algorithm development, which we'll discuss today. This one we've probably thought about the most, which is I have a divergence-free vector field, which is unknown to me, but I observe a solute. So just think you're dropping dye in a glass of water, and in a sort of controlled way, and you'd like to say how much you can, how much information you can get about the underlying flow field from some observation, say in space and time, or you can think of spectral observations, lots of different things. So here's what your target measure looks like. Turns out, so this is an infinite dimensional target measure. This is what we'll often have a Gaussian prior here, which I'll speak about a little more as we go along. This is another model problem, which is to estimate the shape of an inner boundary in a Stokes flow from observing, say, vorticity or some bulk quantities, maybe observing solutes at some points in the flow. And here again, you get a posterior measure. This problem again you can conceive of as being infinite dimensional because the shape of this inner boundary is like a function, right? Okay, and then I rely on very sophisticated computational friends to actually resolve these models. There's, but we have some recently, and I'll use this as an example, some kind of toy model problems that I, as a sort of computational simpleton, can run on my own laptop and get some meaningful statistics in a matter of minutes or hours, and just using simple code that I could write on my own. But this has been a nice model problem, and you can see that you get very, very interesting statistics here. So this is, I imagine that I have an anti-symmetric matrix. This is sort of a toy model in my mind for steady version of the advection diffusion problem. And I want to estimate the coefficients, or the coefficients of my anti-symmetric matrix from observing the solution of this problem in some directions. And so this is the sort of posterior measure you get. I've got a Gaussian constraint on these parameters, which are the coefficients of the matrix, and there it is. Okay, and these are the different. These are the the marginals of the different coefficients along the diagonal, the one-dimensional marginals and two-dimensional marginals. It just gives you an idea of some model problems that are there. There's all sorts of. I mean, you go to your favorite. Your best friend in the chemistry department, say they'll have model problems for you, but these are sort of the set of problems that motivated us working our way into this subject. Okay, and just to very briefly mention this wider say research program that Justin, Cecilia, and I have been pursuing very intensely in recent years. So we're sort of developing a gallery of these model problems in fluid measurement. I mentioned two of them, and they serve as benchmarks for newly discovered, including now MCMC methods that we're discovering, but also as opportunities for applications in their own right. And some really interesting analysis problems appear in terms of, let's say, studying dependence on data, and actually this consistency problem is very, very interesting, which is what happens when the number of observations go to infinity. Can you rigorously prove, essentially, as you would say it in your statistics class, can you obtain the true parameter as n the number of observations go to infinity? And so this algorithm development and analysis came along as part of this wider program. I'll just mention briefly that studying mixing rates connects with some techniques we've been using for the studying invariant measures for SPDEs, some probabilistic techniques, weak Harris theorems, which Peter assured me were not actually due to Harris, but and we have some nice methods upcoming to quantify bias that comes from sort of certain incorrect algorithms that you might want to use nevertheless, that I think we'll speak about in a future date. Okay, so this is maybe insulting intelligences. We're developing our theory in general, so I'm just about ready to tell you about this sort of main theorem of the talk. We're developing this theory in general in the language of measure theory, so I'm just reminding you what absolute continuity of measures are in the Radon-Nikodym derivative. So if one measure measures 0, then the other measure measures something 0, and you get this sort of unique function so that I can describe the one measure as an integral against some function uniquely defined with the other. And then this notion of push forwards, which you probably saw as well, which is basically to say that if I take a random variable and I take a function of it, the push forward of the distribution of the random variable is the distribution of f of x. And as we go along, I mean, some of these you will have seen in your basic classes. Some of them maybe other people knew these, but we derived on our own. It's various sort of calculus identities to actually manipulate these objects. And so we'll see concrete expressions as we go along. And in this context of Gaussian measures for the infinite dimensional case, which we're quite interested in. How am I doing on time?
I think you started
like
about
15 after.
15, yeah.
Okay.
So
I got about a 45 or something, or
yes.
40.
You're roughly speaking, but I Bob Guralnick teaches his graduate course in this room at 4:45. So I think there will be a final
Okay.
time.
All right,
But otherwise,
I'll transition straight to group theory, which I have. Yeah. Okay. So here's our main theorem, and what this is giving you is a sort of one theorem which describes basically any Metropolis-Hastings algorithm you could imagine, and all sorts of algorithms to be sort of discovered. So basically, you have your target measure. It's defined on a general measurable space, and you have an axillary space y. Okay, so I said that there's two elements to these problems. You have the proposal, and you have the acceptance mechanism. So we define the proposal. We have a proposal kernel, which acts, which for every point on the space X gives you a distribution on the space Y. So that's my current point is Q. I draw a V, and then I push the 2 points forward according to a map, which is an involution, which just means, if I iterate the map twice, I get back to where I started. And I require that the push forward of this compound measure, which comes from the target measure and the proposal kernel, is absolutely continuous with respect to M. Okay, and so what the theorem says is if I have something with this structure, then I'll tell you what the acceptance probability should be. It's defined in terms of this Radon-Nikodym derivative that I have here. And this is the resulting Markov kernel that I have. And with this, I'm going to get a Markov kernel that's reversible with respect to the target measure, which is a stronger condition than invariance. Okay. So let me just, you sort of over time, did I go too far? So you sort of over time learn to read these statements in terms of algorithmic statements. So basically, again, wherever I am at Q, I draw, let's say I'm at QK, I draw a VK. I take QK and VK, I push it forward according to my involution. This is, and then I look at the first component, and this is my proposed QK plus 1, and then assuming that under the assumption of my theorem, this Radon-Nikodym derivative exists, you have to figure out how to compute it in different concrete situations. But if I've figured out how to compute it, then with this probability, I take this new point, and otherwise I just stay where I am. Okay, and I'm just reminding you, it's a little cute calculation that reversibility implies invariance. I think of this as sort of the Markov chain as being more, requiring the Markov chain to be somehow more connected. Maybe that's a bit vague. Okay, maybe I'll say one more word about this theorem as well. That we'll talk about all kinds of concrete. I'm going to kind of take you through some classical examples, and then some more recent examples, and then to sort of some of our newer algorithms. But I can think of this in some sense as being motivated by Hamiltonian mechanics. So you think of this as position space. You think of this as momentum space. This is where, as it's going to play out, is going to be the Gibbs measure e to the minus Hamiltonian, and this is going to be, we'll see this is how much the dynamics change the Hamiltonian. So it's e to the minus Hamiltonian of where you started, or it's e to the Hamiltonian of where you started minus where you end up. Okay, so this is sort of like related to the degree of error in whatever my involution is, which is running the Hamiltonian dynamics. Okay, so we'll see this play out concretely, but that's sort of the big idea. Okay, so this, I mean, it took us a year to figure out that this was the right formulation, but this is sort of okay. So let me say a word or two about the proof. It's a lot of these theorems. It's sort of like it takes you a year to figure out what exactly the right formulation it is, and then you learn how to work with push forwards and with Radon-Nikodym derivatives in the right way, and the proofs are very simple. I mean, the theorem, when we finally found the right framing, is just in a couple of slides. So basically, I want to show this reversibility. Okay, and if you sort of plug things in, I have these two terms in the Markov kernel. So this first term is always going to be reversible in this sense, irregardless of this alpha hat. Okay, So reversibility described in terms of observables has this structure, and so I'm going to somehow have to make use of this involutive structure. So because I have this involutive structure, I can get these S squareds here. This is just S composed of S, and then make sense of the definition of the push forward, and then use the Radon-Nikodym derivative here, right? And so now what I need to see is that this expression basically is alpha of QV, the red expression. And then you start to, maybe this wasn't the way we originally thought of it, but you start to derive various identities on a sort of push, so we sort of develop a push forward calculus. Maybe some people knew about this, but we didn't know where, and we gradually over time you start to develop identities. And so if I just remember what alpha is and carry things through, and again use the fact that this is an involution, you get that this expression is indeed equal to this expression. So I've shown that you have the reversibility in the first term. So maybe you're processing this, maybe you're not entirely, but the point is that they're very simple proofs once we set things out correctly using the right sort of calculus. Okay, so I want to take you through a bunch of examples. You can kind of see how things play out, and hopefully you'll get a bit of a sense of how this all works. So the classic one, which is all the way back to our friend Metropolis, you have your target measure is just an arbitrary continuous density. I guess I want to say that it's positive almost everywhere or something like that. My spaces are just Rn with the usual Borel sigma algebra, and my proposal kernel is any function from R2n to R, which has this nice integrability condition, and then you can have we'll start with some very simple involutions. This is just the flip involution, and okay, so you'll remember, I mean, this is the basics here, right? So if I have two probability measures with one of which has always positive density, then the Radon-Nikodym derivatives are just literally a ratio. And okay, so and then this is what the push forward plays out to be. So you really would like, in many cases, that the push forward be its inverse be volume preserving. Okay. Anyway, so that's definitely true of this flip involution, and here it is. So I've rederived here from our theorem the first algorithm I showed you with the nice pretty pictures.
Nathan?
Yes.
Can I just make a quick historical comment? I believe the original Metropolis algorithm, the proposal was always symmetric. So there wasn't even an involution. And it was Hastings who introduced the possibility of non-symmetric proposals.
That's absolutely right.
Involution.
Yes. And we're weirdos for introducing involutions in this context, but the involution really starts to become important when we want to have a unified picture with this stuff, with the Hamiltonian Monte Carlo approach. Yes, that's absolutely right. It's Hastings who added this non-symmetric part. And I think the next algorithm I'm going to talk about actually is the Mala, which is very poorly named. I'll make a comment about that. But there you would need this non-symmetry to derive it out of the Hastings setup. But thank you, Peter. That's absolutely right. That's absolutely right. And actually, previous to us, we weren't the first to think about these Metropolis-Hastings kernels in terms of general measure theory. And so there's a nice theorem due to Tierney in the late 90s. And just to say that along the same lines, you can derive his theory as a special case of ours. And in fact, we're able to derive a second proof of the result I showed you by sort of, in some sense, two applications of Tierney's result. So that we have a whole elaboration in our work on the relationship with this work. But just to mention that this Metropolis-Hastings had already been generalized in some ways to more general measure spaces. this was sort of a starting point for some of the initial work on thinking about how to derive good samplers when your target measure is theoretically infinite dimensional. I'll make more comments on that. All right, so here's this Metropolis adjusted Langevin algorithm. A terrible name. I guess no one spoke Spanish who was working on this at the time. But the idea is, okay, so I have a Langevin dynamic. Okay, so it's this stochastic differential equation in this sort of gradient form. And then if I write down the Fokker-Planck equation, which involves densities, hopefully I've done this correctly and was paying attention in my SDEs class. And so if you just plug this, density into this right-hand side, you'll see that you get 0, and so you have an invariant measure. So this suggests, like, okay, let's do some kind of numerical approximation of this SDE, and maybe we can derive an efficacious algorithm. So my spaces, again, X and Y are Rn. Again, this wasn't thought about initially in the extended phase space way, and so I'm thinking my proposal kernel is somehow generating each step of each increment of the Brownian motion, right? And so I have my effective, I have the sort of position piece of my effective involution written down for me as one step of this Euler-Maruyama scheme. Delta is or delta squared is the size of my time step, right? And the way our theory plays out under some general conditions, where it's an observation that if F is invertible in V for every fixed Q, I can write down an effective involution. And so with that, we're able to write down what the Radon-Nikodym derivative is. If you're looking very carefully, sort of seeing that we don't have, that this is a volume preserving object, I'll just sort of show you, maybe it's somewhat less mysterious in the way we're able to write down this general involution from knowing what one piece of it would be. Okay, and you can kind of see that each of these maps would be volume preserving. But anyway, I think one thing that's sort of interesting to point out at this juncture is that, okay, well, this example indicates that although I may have one algorithm, there's multiple different choices of the S and the V that can lead to the same algorithm. So probably the way the original, and maybe this is in a way to Peter's point, the way you derive the original Mala algorithm would be in terms of the non-symmetric Metropolis-Hastings setup. So I can just think of this as my proposal kernel, right? So it's sort of a Gaussian proposal whose mean takes advantage of some of the local structure of the target measure. That's another maybe vague way of. Okay, so now I want to kind of take you through. So there's a beautiful, there's all kinds of beautiful stuff about Hamiltonian dynamics that you connect with when you start to think about how to use Hamiltonian systems to do sampling. So just to remind you of some sort of simple things that you learned about in like junior high school or something like that, right? So I have a Gibbs measure, which is defined by e to the minus some Hamiltonian. Okay, and I know that if you just notice that, and then I look at an associated Hamiltonian dynamic, right? So the standard one would be, J would be, I think it's 0 minus 1, 1, 0, right? So you get any of a class actually of Hamiltonian systems associated to this Hamiltonian, and you can see that it preserves the Hamiltonian, and it preserves this quantity, which is tells you that Hamiltonian dynamics is quote unquote symplectic, but it preserves volumes important for our calculation. Because of this, the flow map, the push forward of M by the flow map preserves this Gibbs measure. Okay, so I've got my target measure of this form, and I consider the potential here to be like the potential energy for a Hamiltonian system, and my kinetic energy is in this sort of standard form. The C inverse would be physically like masses, and so this gives us a kind of idealized algorithm that you can start out with, which is if I look at the Hamiltonian system, well, let's see, the position marginal is my target measure, the momentum marginal is Gaussian, but I know how to draw Gaussians. Okay, so now I have a nice algorithm which we're even able to show in some contexts are mixing, right? That just in the momentum piece. So wherever I am, okay, I draw a Gaussian with this covariance. Yes, around. This is right. I draw a Gaussian, and then I push this forward in my Hamiltonian dynamics, and that's my this is. I think I was just having a screaming kid in the other room. This is just meant to be mean zero. But anyway, I push this forward, and so I get an algorithm that's exactly holds this target measure as invariant. Of course, I can't just numerically solve exactly this equation. So the question is then, how do I take this idea and what class of sort of numerical solvers for this system will hold that for which we can basically write down a good metropolis. Acceptance probability. Okay, so just a 2-minute tour of geometric mechanics, right? So we have these two properties. So what do we really need for our S? We need the S is going to be something to do with solving this Hamiltonian system numerically. We need that it's involutive, and we'd like that it's volume preserving, this stronger condition simplicity will serve. And so this is so long as R is itself involutive, you get that if your map is R reversible, then R composed with the map is reversible. And then you can do palindromic compositions of a bunch of maps that are R reversible and get another R reversible map. And of course, compositions of symplectic maps are themselves symplectic. Here, again, this should be a phi n. Okay, and then sometimes you can see these things by hand, right? By taking a particular map and literally just observing these properties by hand. But we also have a more general thing, which is that if I have a nice Hamiltonian system, it's symplectic, as I sort of showed you in the last slide, and it's reversible with respect to momentum flip involution. So these are little calculations. So what this means for you is that you have a means of deriving algorithms, and you see that, let's say if I take the Hamiltonian and I split it into multiple pieces, and then I know how to exactly integrate each of the pieces, don't kill myself walking around the room, then I know I get a symplectic momentum flip reversible map. So this is our expression of this algorithm, which goes back to these statistical physicists, and then Radford Neal in the 90s introduced this in the computational statistics community. So my spaces are both position momentum space, are both Rn. That's why I called them as such. My proposal kernel is just this Gaussian, so the momentum marginal of my Gibbs measure. Okay, and so these two maps, which come from this splitting of the Hamiltonian, indeed maintain these two properties. You can see this by explicitly seeing that they solve Hamiltonian systems, or even just checking by hand. And so if I take this so-called leapfrog splitting, this is the most classical case, I get this acceptance ratio out of my theorem, which is what you see in all of the nice textbooks. But what I in my little thumbnail show, you have a whole kind of class of possible integrators you could use. And in fact, we developed in the paper, some of these things were observed previously, but that you could basically completely disconnect as far as having an unbiased algorithm in our theory, the numerical trajectory, the structure of the numerical trajectory with the target measure. So this is sort of just one example of a whole huge class of possible algorithms you could work with. And as we'll see, I'll mention this, like computing gradients of U in many cases is a monstrous task. So maybe I want to replace this with some kind of nice lower order approximation, either from the existing samples or using something we understand analytically about U, which, don't forget, comes from the solution of a PDE in our case. So just sort of wider comments. Okay, so the algorithms that we were working with and trying to understand and generalize came from Andrew Stewart's group in a series of works about a decade ago, where they realized that you could write down versions of these algorithms that made sense at the infinite dimensional level directly for measures that were absolutely continuous with respect to a Gaussian base measure. And so you sort of see that these dynamics can be shown to be invariant with respect to certain preconditioning here. So this is not exactly the same form as I wrote down the Mala algorithm originally, and so there's these have proven to be very efficacious for the type of problems that I showed you at the beginning. I think I wanted to say one other thing. So the idea is, in the end, you're going to have to discretize or look at a finite dimensional version of these measures to actually run these approaches. But what you should find, and we can show in some cases theoretically, that the number of samples you should have to take should be independent of your discretization level. Okay. So what that means is that you partially address the cursive dimensionality by looking at dynamics that make sense directly at the infinite dimensional level, if that makes sense. Okay, so I'll just, again, this is supposed to be a colloquium, just a very brief, some brief remarks. So we have a really nice theory of Gaussian measures on Hilbert space. You may learn about this in the course of your graduate school education. And so we're just saying it's a Gaussian measure if any push forward by any bounded linear functional is normally distributed, and you can write down what the mean and covariance means in this context. You can write down and uniquely characterize characteristic functionals. And what for us is nice is we know how to write down Radon-Nikodym derivatives as a sort of special case of it's called the Cameron-Martin theorem, and you know how to actually simulate these random variables if you know what the spectral structure of the covariance is, which we can set these problems up in interesting ways where we do. Okay. All right, so this is the first of these algorithms, which is based on the fact that the proposal kernel is actually invariant with respect to the Gaussian measure. So you end up with a push forward that's absolutely continuous with respect to the compound measure here, right? So and that comes from the fact that without this likelihood, I call it a likelihood piece of this measure, what I call M naught is invariant with respect to this compound. M naught is invariant with respect to S star, and then so it's a simple exercise. I feel I'm running a bit short on time to see that this is exactly what you're going to actually get. So this is sort of my last example here. Here's the algorithm. It's very so we have a multi-proposal version of this algorithm that we think may be very nice. Sort of generalizes this proposal structure. I'll talk about just at the end. But the idea is wherever you are, you kind of take some combination with this rho, which is rho you can think of as degree of aggressiveness between your current state and some proposal according to this Gaussian measure here. here. And this is what your acceptance probability looks like. So we'll see this play out with some examples. All right. So I'd say the algorithm that started us down the rabbit hole, which led to the theorem, which I showed you earlier, which was this infinity HMC. So again, we're looking at target measures with respect to Gaussian absolutely continuous with respect to this Gaussian, I call it a prior because you think of this as the prior, and this guy is going to be the likelihood in these Bayesian inverse problems I'm pointing to. And you can show that this preconditioned sort of non-standard Hamiltonian dynamic holds the Gibbs measure as invariant. And so they have a particular leapfrog, leapfrog splitting of this Hamiltonian that they use in these works and in reference. So what started all of this, in fact, is basically each time that I compute a gradient of phi, I'll show you this in a slide, I'm doing a PDE solve, right? So we wondered if we could replace this with approximations and how much flexibility we had to replace these gradients with approximations and running forward this dynamics. Essentially, what can I replace this with as far as an approximation is concerned? So in trying to justify what was originally an appendix is ballooned out into this paper and this theory, which we're very, very satisfied with. So that it was this algorithm in particular and trying to understand it properly and see these beautiful works treated this algorithm using sort of finite dimensionalization arguments reminiscent, and they said this explicitly, kind of inspired by these works of Bourgain that treated the invariance of the Gibbs measure for various Hamiltonian PDEs. But we sort of didn't understand why these arguments were working in the way they were, and especially with this idea of approximations. And the scope of approximations of these guys was what sort of led us down this path initially. Okay, and I'll just sort of briefly gesture at the fact that just think every time you evaluate a phi, you're doing a PDE solve, and you have to develop, sort of use integration by parts to even be able to reduce a gradient to a single PDE solve. So you sort of have one PDE solve per evaluation of phi and two PDE solves per evaluation of gradients of phi. And say you want to run this dynamics over a window of time. So okay, so I'll just mention too, by the way, that this system you can prove, even though you wouldn't expect that the Gibbs measure would be mixing with respect to the extended dynamics with this momentum resampling, you can prove mixing results. But I think I said something about this last time, and I don't want to go too far down this rabbit hole. I just want to say that the question of mixing of these for these algorithms, I think, is a very interesting one, and you can address with methods of, I think, came up first in the sort of SPE world, which is where I've come from. Okay, so here's this algorithm, this first algorithm I want to mention today that sort of fell out of this theory, right? So the question was, again, what could we replace this gradient with? And the answer was, in the end, basically anything we want. And this is just one example of a possible splitting one could use. Okay, so there's all this flexibility in the choices of parameters, which is just this sort of whole space to be played with. So what's sort of nice about this theory too is that with special parameter choices, you see that that this infinity mala and the PCN falls out under special parameter choices. And in fact, in an earlier, as we were working on this for examples, Justin my collaborator was running code where he had accidentally turned off the gradient and he was getting the correct statistics and we didn't understand why. And this explains what, so he was like computing the gradients and then not basically plugging it in here for some computer bug essentially, but getting the correct statistics, and we just kept shrugging our shoulders, okay. But this actually falls out as a special case of whole class of algorithms. So it sort of explains strange behavior where things seem to work. It's one of the strange things about this business actually running these on examples is sometimes things that you can tell aren't working work better than you think they should be working, or things that you don't think should work are working, and then you have to figure out why. But anyway, and just to say that again, okay, so we can kind of see this involution structure by hand with this sort of thumbnail description I gave you of sort of geometric, some ideas from geometric integration theory, and then careful and repeated use of Cameron-Martin theorem, some characteristic functions, and just these nice identities which you start to observe for these push forwards. All right, so maybe I can just spend a few minutes on these multi-proposal methods. I guess I'd like 5 more minutes if
5 minutes.
If Robert. Okay, so basically, as I said, Andrew was a kind of silent fourth co-author on this first work, and he's very interested in parallel methods where instead of generating one point, you generate a cloud of methods. It's very natural for, if I wanted to sound fancy, working with GPUs, and he's actually even has potential applications in quantum computing, but okay, I don't with these multi-proposal methods. And there are other sorts of acceptance probabilities. You want to have the structure where, let's say, pi is related to either the density of the target measure or something like the likelihood. And so if you generate this cloud, you'd like, if the cloud lands on a high probability area, you have a high probability of accepting. And this is called a Barker type acceptance probability. So we have a multi-proposal version of the PCN algorithm, which I'll maybe show you in 2 seconds, some experiments we've been doing with. And then we can think of this, and we've thought of this as another sort of gradient-free approach. In the third example, or the second example I showed you where we're estimating boundary shape, we think we can write down an adjoint method, but basically anything to compute gradients is going to be potentially hell. So this is maybe another alternative to computing gradients of the solution map associated with these Bayesian problems. Okay. So one takeaway is that some aspects of the theory that I showed you before just generalize very nicely to this multi-proposal setting, right? So basically, instead of one involution, I have a collection of involutions and a collection of alphas. And now I want the alphas to satisfy some algebraic identity, which is sort of what you needed for the theorem. Okay, so the multi-proposal version of this, our previous theorem, falls out as a special case, and you get sort of Metropolis-Hastings type acceptance ratios falling out naturally. So what takes us a year of playing around with identities and looking through various specific algorithms in the computational statistics literature and trying to understand what's going on is to figure out a setup where we get a more useful acceptance ratio in a fairly general way, which this theorem, as I'm assaulting your eyeballs with, has this sort of multi-proposal version of PCN falling out as a special case. But basically, we have a very special class of proposal structures, which we call conditionally independent proposal structures, which take this particular form, which is at the current point, I generate 1 point around it according to one kernel. And then from that new point I've generated, I generate independently a bunch of points, P of them, P being in cases that Andrew computed 10,000, 100,000, okay? And then so long as Q and Q twiddle satisfy this relationship, right? With respect to some base measure, which is absolutely, for which our target measure is absolutely continuous, I get this nice Baker-like acceptance probability. So the takeaway is that after a lot of trial and error and thinking about this down a lot of rabbit holes for a long time, we're able to see we're able to get an acceptance probability that if one of the points lands in a very high probability region, we're gonna have a good probability of accepting that. And okay, so this is like the generalization of the random walk Monte Carlo. You can see how the algorithm goes. I have my probability density. This generalizes this work of Tjellemond, which sort of initiated this, where you have R is again a Gaussian proposal around your current point. But this just shows you can kind of generalize this to an arbitrary probability density. That's one. And then the PCN, which allows us to think about these infinite dimensional problems from a multi-proposal standpoint, is as such. So basically, this was the same proposal kernel that was in one step of the preconditioned Crank-Nicholson algorithm. Okay, so around our current point, we draw one point, and then from there we draw a cloud of points, again using the same proposal kernel. And here's what our acceptance probability is going to look like. Oh, and I can mention too, there was a whole other aspect of the theory which we developed, which I think came out quite nicely, which says in essence that if I want to generate this cloud and generating these acceptance probabilities, each one of these, think of it as a PDE solve. So I've already done the work, and maybe if I generated a cloud of 1,000 of them or something, maybe 10 of them are actually in a high probability region, right? So I can resample this cloud as many times as I want and still maintain an algorithm that's unbiased. Okay, so maybe I'll just say that we did some numerical experiments with all the examples I showed you. This is to say that we get some interesting, suggestively good convergence results for MPC, and this is maybe the most visceral, right? So this is the time series of, say, the norm of Q in whatever color you'd call this chartreuse, and then purple is just PCN, right? And so there's all sorts of, this is just like the beginning of the story. You'd like to run all sorts of parameter studies for this. Maybe because I am running short on time, I won't speak at length about this other example, but this kind of shows you at I love this picture. It goes back some years when we first generated this, but this shows you the Fourier modes of the unknown velocity field and sort of like the marginals onto two Fourier coefficients. And you can see, the 2-point correlation spatially in, say, vorticity. So these measures are giant boxes where all sorts of, so this was to show you that we implemented this MPCN and had some promising results for this model problem, which we had previously simulated using PCN and the infinity HMC algorithm. Okay, so I'll just make some closing comments, right? So I think that there's a very satisfying top-down picture which we obtained from our theory that sort of links together all these different algorithms, and you sort of see how they're related to each other, and it provides you with a kind of cryptic maybe to derive all sorts of algorithms. And in particular, this sort of surrogate, we wouldn't have called this that at first, but it's sort of surrogate trajectory methods that I showed you. And this MPCN falls out of this sort of general top-down picture, right? The multi-proposal setting is promising for high-performance computing architectures. That's certainly above my pay grade to be implementing, but it sort of shows that maybe there's promise for this for running if you have an industrial level application, right? And so we're in the midst of carrying out more case studies. I think these are very nice problems for graduate students who really want to compute. I've had one who was incredible with this, but anyway. And then these little toy models have allowed me to actually play with this on my, it's like having I think of it like the difference between having like the industrial lab and having a little tabletop lab that you'd have at home that you could try things out with. I just mentioned rigorous estimates for mixing rates. I think it's a very interesting problem, and we want to maybe generalizes to the multi-proposal case. And then one of the things that's weird is like in trying to figure out what the right thing was, especially for the multi-proposal case, we spent a year almost arguing about some algorithm that looked like it was unbiased without this actually extra correction step. It looked like it was unbiased. And we were able to finally convince ourselves that there's actually a little bias there, and we don't quite understand why it works as well as it does without the correction step. But I think we have rigorous methods to put some quantification to this bias that we're seeing in these methods. So these are some more general references. I thank you for your patience and I appreciate your attention.
Thank you. I think we have time for a quick question before Bob comes and kicks us off, or maybe he's not. But so any questions? Questions or comments?
I have one question.
Tell me.
Well, for one, I'm way far from understanding every detail, but I have one question about the multi-purpose algorithm. It looks like it depends on this parameter rho.
Are you talking about the
algorithm where you fix rho in 0, 1, and
Yes.
then you have some kind of a rotation between the qk minus 1 and the
Yes.
next one. So at the end, what's the role of that rho in the end result?
So I want to click back. So this row is related. Okay, so the simple answer to your question is that that's sort of how aggressively you're exploring the parameter space, right? If you explore too aggressively, you're just gonna fall way out of the high probability region. If you explore too conservatively, you're just gonna move around the high probability area. So like, if you look at this row, this is the original PCN, and then MPCN has this row appearing as well. So if rho is close to 0.
Close to 1. You want rho to be close to 1 so that you can carry more information from the previous.
Well, you don't want it to be too close to 1, or you're just going to stay where you are. You're just going to stay in your home. But if you make it too far from, if you make it too close to 0, and you're just aggressively exploring around, you're gonna get mostly nothing, right? So in fact, the optimal tuning of this parameter is something that's actually part of the mystery of this whole subject. And okay, so there are all these like heuristics that you learn about from the statisticians. They say you should make this so you get an acceptance probability of 20%, because you write down what the acceptance is, and then you run it and you see how often you're accepting according to that. So you want to be aggressive but not too aggressive. It's like, training your kid. You don't want them to just run wild in the streets, but you don't want to keep them at home the whole time. I don't know. Anyway, we can talk about that later. But that's that. Now, mathematically, this comes from a Crank-Nicholson discretization of a Ornstein-Uhlenbeck process, and this row is related to the size of the time step. But there's a couple of little manipulations that this comes up. But I think my original answer to you kind of gets at the spirit of what this thing is doing.
Okay, I understand the kids part.
Yeah. But honestly,
that's exactly what it is.
Yeah. You want to be aggressive, but not too aggressive.
Yes, of course.
But how aggressive is like the art of the max, which I think carries the thing forward further, the analogy forward.
And the analysis actually gives you some information as to how you can be the right amount of aggressiveness, or does it?
They're super idealized. I don't think anybody knows.
Trial and error.
There's trial and error. There's in the finite dimensional analog of this, the random walk, there is a work by what is the name of the work? But anyway, they tell you what the acceptance ratio should be, but your probability as the number of dimensions goes to infinity, but your probability distribution in this theory is mu of, let's say, x1 through xn. This is the theory, is what the acceptance probability should be for, I think, random walk Monte Carlo. And this is why I don't love being recorded, because I'm going to say something totally wrong. But their theory only applies to essentially, let's say, that each of the dimensions are independent. So it's pi of j going from 1 to n of f of x j, like so. So this is like totally ridiculously idealized. You wouldn't have to do the sampling if this is what it looked like. And so this is kind of like, but there are real opportunities to bring to bear. I mean, a fairly an eminent statistician that I was talking to was saying that, like, you know, in this stats community, there was no, until recently, like the idea of bringing dynamical systems into the picture was a big breakthrough. So there's lots of opportunity, I think, to, you know, especially if you can have good connections with nice statisticians who can give you access to literature that I wouldn't have known about or known how to read. I think there's a lot of opportunities coming from sort of the world I come from to maybe make some helpful contributions. And there's nice PD applications. So, but anyway, yeah, it's often the heuristics that we use to tune parameters is very like, it's a dark art.
So, any other comments or questions? Or Peter, do you have any comments?
I always have comments. So one comment related to the discussion just now is that in the multi-proposal setting, if you don't fix rho for all the proposals but let rho vary somewhat, can you tell from observing which of the successful proposals, or if you sort of randomize rho to some extent?
So
does that mess up the calculations totally? I wasn't following.
I mean, this is a picture that may be interesting, right? So this is like very aggressive. Okay. And in some sense, you want this time series to be more wavy because it means you're exploring the space better. Remember, if you're too aggressive, you go off into, you know, a bad region you never accept. But the multi-proposal somehow, I mean, we don't know what the right tuning of rho is, but somehow what this picture is supposed to be telling you is for this particular problem. I don't know if I'm answering your question, Peter, but what would be a good degree of aggressiveness for the single proposal case is way too conservative for the multi-proposal case. And I have some intuition that that's another kind of indication what makes this gradient free. Like we're each cloud that I generate is going to somehow pick up some good regions to pick. And the structure of the acceptance probability is important here. Now, I guess I wanted to say something else. I keep seeing type of, oh yes, people do adaptively tune rho as you go along. That's often to hit a particular target acceptance probability over time. But there's all kinds of, I mean, there's endless things to play with. What we're sort of doing is setting a clear space in which you can make some. I think Susan's giving me a look like. We're being unfair to
the class is waiting.
The class is waiting.
So, but we can just move to the tea room, and
Okay.
I would encourage anybody who would like to continue chatting, come have tea, or not have tea, but chat in the tea room. And we will be going out to dinner. So anyone who's interested in joining Nathan and myself for dinner, please let us know. And now the topologists are allowed in.
Okay, thank you.